Yeah. So, good evening, all. This is second live interaction session for Aspen Plus course, which is the beginners course, right? So, how many of you were there in the last Tuesday session with me? So there were two sessions last Tuesday, one with me and one with Rajdeep. Okay. Were you there here? Okay. You were there, Chikamuli. Oh, nice. So you were not. It's fine. So there are two live interaction sessions. One is with me, which will be scheduled on Tuesday, 6 to 8 p.m. And then another with Rajdeep, and he has opted for Saturday session. So Saturday 6 to 8, he will be taking this live interaction session, right? So both of us will have a different approach. Anyway, so we can begin with. So only one person was there in the last class. Uh, So let me just briefly introduce myself. I'm Bhavesh Moorjani, a third year PhD student from IIT Bombay. I'm doing PhD in the Chemical Engineering Department at IIT Bombay. Regarding my Aspen Plus experience, I have done Aspen Plus course in my UG curriculum, where I have used Aspen Plus. And then after that, I opted for this NPTEL live interaction session TA duty, because this was also part of my interest to uh, teach and relearn Aspen also, right? Mm. Now, before starting ahead, I will just I wanted to first ask you how many of you have gone through week two lectures, because there were multiple things covered. So I want to know what are your thoughts and what are your expectations from this live interaction session. What you want to learn for that week two part. Have you all gone through week two lectures? Can I get yes or no? Not all. Okay. So I assume you have gone through one or two lectures. What about rest of you? So I'm asking this because there are multiple unit operations covered, and if I want to, you know, even give you a recap, it will be difficult in this 2 hour sessions. So the way I have planned is that I will cover the first two lecture, mostly first two lecture part, mixers, splitters, heat exchangers, separators, and then after in the columns part, I will be discussing extraction column, and if time permits, then we will discuss about the distillation column parts also. Okay, that was one thing. And another thing, how many of you have installed Aspen and started doing some simulations in the Aspen? So, Abhijit, what about rest of you? You guys got a access for Aspen, right? Gaurav Baba. Okay. Uh, yeah. So I might be needing your help in one or two simulations because some of the package in my Aspen version are missing. So in that case, Nishu, if you have some issue with installation of Aspen, I will suggest you to contact the NPTEL team. Since the license is provided by IIT Guwahati, so there was this Google form, right, where you can submit what issue you have during the installation process. So you can write to them and they will answer you. Okay. And if still issue is that, then you can mail me. I will contact them for that. Okay. Database configuration related issue. So what you do, if uh, let me share my screen and show you. Yeah, so I hope my screen is visible. So it was last Tuesday, right? Huh, so you have this link, right? Three different links for the software installation, and this is for documentation part. And if you have an issue with the installation process, go to this link, fill out this Google form, upload an issue that you have if you have a screenshot or video recording, and then NPTEL team will get back to you related to the issue. Okay, so that would be resolved. If not, then try to contact me. You will have my email address. I will try to contact you from NPTEL. Okay, that is one thing. So let's start discussing and revising the week 2 part. So this is the brief introduction of me. You can find the details, like if you want to contact me for any discussion part also, you can contact me via this route. So in the week 2 part, sir has covered mainly various unit operations. So that are this mixers, splitters, separators, exchangers, and columns. Okay. So what I will try to do, I will try to cover this first three aspect, and then column, if we have time, then we can look. We will look into that part. Else, I will try to cover it in the next time. Okay. So if you will see in the Aspen Plus, in the simulation part, so we have this mixers, separators, exchangers, and column, right? Out of which these mixers and splitters are used to, as it says, to mix a stream or to split a stream, where composition of the streams doesn't change, while the separators are used for this separation of vapor liquid or liquid liquid separation, right? Where composition of your feed will change. Then you have exchangers for heating application for heat transfer, and then column. In the column part, as sir has discussed, that we will be pertaining, like we will be sticking to only this first four aspect, that DSTW, DSTL, red flag, and extraction column. This column, these are used particularly for petroleum applications, like for a higher fraction that we won't be covering in this course. So if we start with the mixers and splitters, as you can see in the mixers and splitters, we have three columns: mixer, F split, and S split. So first, let's understand what is the difference between these three. So anyway, yeah. So mixers is used to separate more than one stream, like sorry, mix the one stream. Like, so your input can be one or one, two, or three streams, and then you can provide outlet in two parts. So for the mixers, let's say you have multiple streams coming in your mixer, and either you can provide output as a one mix stream or a second decant stream. So you can use mixer in two way, either to just mix or also to separate a decant stream where a heavy component, like let's say heavy density component, will be separated from the bottom part. And then if we have in the splitting, if we have a one stream and then we want to break it into different parts, let's say stream 1, and I want to create second, third, and fourth stream, right? Then you can use S split or F split. The difference between S split and F split is that the how much, what should I say, the flexibility you have over the desired output. So S split uses only two parameters: either you provide split fraction or the flow of this three streams, and then you will get a split fractions. While F split has a other parameters such as limit flow and cumulative flow that are useful in terms of controlling the desired output. So we will discuss that also. Let's consider this example. So some of the example I'm using in today's lecture are that what sir has taught, and some of the example are new. So first start with the basic example where we have this water, benzene, and toluene, three streams coming in together, and then mixing in. First they are mixed, and then we separate it again into the three parts. Okay. So first what we need to do, as we start a new simulation, we need to specify different components, what components we have here. So here we have three components: water, benzene, and toluene. So let me quickly add it. I, I assume that you guys are familiar with this property selection and the specifying the different component parts, because that was covered in the first week and it was also discussed in the last interaction session also, right? Mm. Sorry, benzene. So we have added the components. Let's select the method. So for the method selection, I'm using right now this SRK method, right? And Steam NBS for the selection part. These are the method that sir have used, so I'm following his part only. There are some missing interaction parameter between toluene water and benzene water. Then you can use this estimate using unified method and then run a property analysis. So it will calculate the missing fact, missing parts. Let it run first. Let's see processing. Please bear with me because of this recording and also the online session and plus this Aspen running Aspen plus it's running slightly slowly, but we will cover it. Result available with warning by results. Calculation by completed with warning checks is equal to 2. They are not in a data bench of data. I guess this should not affect our results. So previously, one student was asking about how to save the data for any property. So let's say you are analyzing one property for a pure component. I want to see the some density variation of rho, density variation of toluene, right? Gram process from 0 to 1000 degrees centigrade. So when you do run analysis and when plot will be generated, so it's running. Sorry. Uh, Let me restart it. Can you guys wait for a few minutes? should not have them. Guys, can any one of you share your screen, whoever has access to Aspen Plus, so we can try sample example in your PC only. Since because of the recording, I guess I am facing this issue of Aspen Plus not working well. So any of you want to do volunteering? Don't worry, I will tell you what you have to do. Hello. Uh, then has anyone access to the Aspen Plus right now? Yeah, Shubham. Can you share your screen if you have access to the Aspen Plus? Hello. Shubham, if you have the access, can you share your screen? Okay, you are installing it in that way. Yeah, Gaurav, do you want to say anything? Meanwhile, let me try it again. What I will do is, I will just open the example. Okay, yeah. Thank you, Gaurav.
Yes, really?
It's visible. Now go to the Aspen Plus. So we want to add three components: water, benzene, and toluene. So can you add it? Click next. For the method, here we are selecting the SRK method. So in the base method, select SRK. And the free water method, so select steam NVA. So below this SRK method on the left hand side, yeah, steam NVA, C NVS. Do next. Estimate using Unifac and run.
Next, right?
Next. Yeah. Run property analysis. Okay, result available. Now go to the simulation tab. So see, here we have three model, right? So first, drag the mixer model. Uh, Now add three material streams to this mixer model. Okay, and then one outlet stream. So here you can see in the B1 block there is small blue line, which is an optional stream as a decant stream. So if we want to specify a decant stream, we can use it, else it's fine. Now add add stream data. Press next. Can you go to the home? So first we want to add stream 1. So stream 1 is water at 80 degrees centigrade. Select pressure value as 1 bar. Mass flow rate of 1000 kg per hour. And select fraction. Select mass fraction as water as 1. Press 3. Next. Benzene at 70 degrees centigrade. 1 bar, 1000 kg per hour flow rate. add mass fraction as 1. Yeah. Then third stream is toluene, again 1000 kg per hour flow rate and 60 degree centigrade temperature. So toluene, it's toluene 1, that will be 0. Go next. Now it says that required inputs are complete. So we can run the simulation. Do okay. So it's running the result. Now, so it's processing it. It's still running. It should not take that long. Okay. We can wait for a few minutes. Deepak, if you are having an issue with the installation process, try to contact the NPTEL team. We have received, if you have received that mail for Aspen Plus installation also link, there is one Google form link also. If you have issue, put a screenshot and then submit it to them. Or you can ask some of the people also who have installed the Aspen Plus. So how they have installed it. Right? Since I'm not using the license provided by IIT Guwahati, rather I'm using the license of IIT Bombay. Yeah. So results are available. So can you go to the result log? Go down. Stream results. So here see, scroll down. First, can you go to the mass flow? So we have 3 streams, 1000 each, which are coming together, and we have final value should be 3000, obviously. And if you will see the mass fraction or mass fraction, do plus on mass fraction. So each stream, since it's mixed, so composition will be uniform. Everything is 1000, right? So we have uniform composition. But what you will see, if you will go up in this result block and try to see the temperature on the top, in the result block only, see temperature value. So we have liquid phase coming at high temperature of 80, 70 and 60. But the outlet temperature is minus 15. So should it happen? No, right? So there is some issue with the method that we have selected. So for that, how will we identify? So go to the mixer block B1, input parameter, click that. See, now here you have two options. Although these are not required options, that's why we were able to run the simulation part. But still, because of some this parameter, we are getting the temperature value of minus 15. So the reason is that the valid phases that we have chosen. So can you click on the valid phases option there? So here we have various options. So now see, we have feed coming, like feed is water, benzene and toluene. So it should be a combination of all three. Now you have option of vapor liquid free water, liquid dirty water. So if you will select vapor liquid free water, select vapor liquid free water. Yeah. So why vapor liquid free water? Since we have this mixture of benzene and toluene at high temperature, it might generate a vapor. And water, as it's a heavy component below its boiling point, it will be present. It will be kind of in a separate form. So that's why we are selecting vapor liquid free form. And if you will run this now run the simulation with this value. Okay. Result available. Can you check the results now? Stream results. Huh. So see, now the temperature value has changed to 53.3867. So when we are using this different models in this Aspen Plus software itself, so each model, like, they have various specifications by different methods by which they calculate. So we have to be thorough what kind of method we are using while calculating this process. So this was this example of simple mixing. So when we knew that three phases will mix and thousand each, we will get 3000 value. But temperature values were wrong because of the calculations that were like the phase equilibrium calculation that it was using was wrong. And when we change it, we are getting the right value. Now, uh, my Aspen Plus has started. So if you uh, it will be better if you stop it and I can continue there since I have already things preloaded. Yeah, thank you, Gaurav. So,
No, excuse me, sir.
yeah.
Sir, there's an issue. No, opening Aspen. The thing is, my laptop is running graphics and the specs are these are just matching with Aspen bones, but it's not responding it. It's like it takes about if you have such a component, it's there's some examples.
Hmm.
Just if I touch it, a white screen came and it's mentioned like it's not responding. I am facing this issue since May 1st.
So, have you tried to contact with any of the NPTEL team? See,
Yeah, I have sent mails.
you have sent in mails. Wait, they generally respond. So, one thing could be, are you when you are running Aspen Plus, you are running Aspen Plus only, or you are using any other software while in parallel? So, for me,
No, 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 just Aspen.
just Aspen. So for me, when
Yeah.
I'm just using Aspen Plus, it works. Yeah, it takes time to do some calculation, so that buffering is there. But if I'm doing heavy tasks, like currently I'm recording also and doing simulations also, then it will not respond well. So that could be one thing. Specification wise, if your laptop has good specification, it should handle it. Have you installed few packages or all the packages of the Aspen Plus? That could be also one reason that uh, it might be taking load on your PC.
I have installed Aspen that mentioned PDF.
Okay. So you have already contacted NPTEL team. What I will do, I will try to go through that manual that they have provided and what's the installation process there, and then we'll get back to you guys because I'm not sure. I'm using the IIT Bombay license and it's working fine for me. I haven't bothered about looking into that licenses. So
Yeah, it's using the license is getting expired August 15.
Please send a screenshot of your concerns to NPTEL team, specifically this Google form which I was showing you, right? So, if you have any issue, send it to them, mail it to them. They will reach out to you with this solution.
Okay, you mentioned it
Yeah,
because uh, I have a good laptop, Asus F15.
okay.
So, uh, previous meeting during was and they mentioned it should work properly on your laptop.
Yeah, it should work. Yeah, if, specifically if you have a good.
And think the thing is, I am joining this course second time because first time I was a fresher, and the second uh, yes. So I was on the software having me. I will choose my laptop. This time I installed this software, but it a file comes like MX or I don't know. But it contains every file within 1 KB. So it's playing, but it runs my old software.
So Tawshif, right? Can we discuss this
Yeah.
later also because since we have other things to cover. So after the session, we can discuss it out. Your problems. If I'm able to resolve it, else I will definitely try to contact NPTEL team that people are facing these issues. So if you can look into that, right?
No, no.
Yeah,
Yeah, sure. Sorry to
got your
disturb you.
point. No, no, it's okay. But since we are running out of time and this simulation will again take load on my PC also.
Okay, no problem. Thank you so much.
Yeah, you're welcome. So, as I was saying that, yeah, yeah, if I have results right. So in this main flow sheet, I have so right now just focus on this first three part, like first three mixer part. So we have water, benzene, toluene coming to the mixer, and they are mixed together. So as I was saying that the method that you have to choose, the phases that you have to choose, you have to be very careful. To in order to understand what are the these various phases and what does it mean, you can use the help manual. You can try to search on the Google itself. There are various forums also available, which will help you to understand which method works. Like for example, for mixer, I don't know what are the valid phases. So I'm just searching mixer valid. Mm, oh, sorry. This pixel. So you can see specifying mixture, uh, various options related to the mixture. So that is, you will find some sort of a guide which method to select when. So here we have free water also present. If you have solids present, then you can opt for this solid only method. If it's a mixture of kind of thing, solid plus liquid or vapor plus liquid, and how many phases you have. So here, see, our system contains in a way two phases. Since water is a heavy component compared to benzene and toluene, in a way phase separation will happen. So in a way, although it's a liquid phase, and depending upon the temperature, you might get a vapor also. We have two phases. We have free water also. That's why we selected this method, and based on that, we got an answer. So selection of the method also becomes important in such cases. So be aware about it or what you are doing there. So this is a basic example of mixer. Now then after mixture, if you want to split a stream, so we have two options, F split and S split. Now why we need to split a stream? Suppose after the processing of your product, let's say from the reaction stage you get some mixture of products, then you was do series of separation operation, either be distillation, adsorption and everything. Then after you get a product, so that product we send it to various plants. You might send it to storage unit, you might send it, you might recycle back into your reactant stream for increasing productivity. So in that case we use this splitters, right? So in this Aspen Plus, this mixer and splitter they are modeled as a unit. But in actuality, this thing might not be a unit. You might have three pipes coming together, forming one outlet. That is your mixture. Uh, you might have one product outlet stream, splitting into three parts. That is your splitter. So it doesn't have to be a dedicated unit. Rather, it could be a simple piping network also, which is separated into two parts. So here uh, we have this F split and S split option. So if I go to this B2 and B3 block, B2 is F split. So in F split, you have various options to specify the output. So here I have selected, what I have done is, first I have used this manipulator duplicate. As sir has taught in the class that you can use this duplicate option. So what it does is that it's a string duplicator used to copy a string to any number of outlets. So the mixture output, I am duplicating it and using in both FS split and S split for a comparison. Now, for the uh, B2 block, which is FS split, we have multiple options. Either we can provide split fraction, we can provide residue fraction, or we can provide this limit flow or cumulative limit flow. So why these two options are useful? So if we have some specific requirement of split fraction, let's say out of your product, it is needed that at all the time 50 like let's say 1000 kg of mixture should go into this storage unit, 800 should go into some processing unit, and you want to maintain it regardless of what fluctuation happens into the prior stage. So if it happens that your process has some fluctuation and then your feed flow rate goes down, so instead of 1000 benzene, 1000 toluene, 1000 water, you are getting 700 benzene, 600 toluene. In that case, what should happen? So what we want to do is we want to fix the output that my S5 stream, if I consider it as a uh, what should I say, storage unit, saying that it should have a fixed fraction. So here I have provided, so in F split we are using splitter to split into three parts, S3, S4 and S5, and the output are provided. So right now I have used split fraction, so instead I can use limit flow. In limit flow you can mention the flow, so let's say mass flow, and we want that 1000 kg should go into S3 regardless of what happens. So now you have to give it an order, like what will be your preference. So stream order. So first it will try, if any fluctuation happens, first your stream splitter will try to put this 1000 kg first, and then it will distribute other parts. We can put other condition also that limit the flow. I want that 500 kg should go into the second stream. So in the S4 stream. So I have provided this condition. While for the S split part, if you will go into the input, you only have two options. Either you provide the flow or you provide the split fraction. So for all these streams which are connected to S split, I have provided various parameters, like for S6 I have provided 0.25 fraction. This is just for an example. Okay. So you just provide a composition and then it will split it. So if I run it, particularly we are interested in this B2 block. So stream results related to the B2 block. So what we had said that first priority should be stream S3 stream where 1000 kg of flow is needed. Then S4 and then rest can go to the other part. So that is a limit flow. Now let's say your feed condition changes. Here in the input part, instead of 1000 you have 500 kg of benzene coming. Toluene goes down to 800 kg. And water goes down to again 500 kg. Okay. And with this condition, if you run it, result available. So Let's check the result of this B2 stream. So again, what it tried to do is first it mixed the all three stream, and then first priority was S3. That S3 will should have 1000, then S4, and then S5. So this is how it has distributed. So the use of this F split and S split, these are very simple unit. It doesn't have much significance, but then you can use it for a various what if scenarios. What if the flow of the feed falls down? Then what will happen to the various streams that are going outside, right? In actuality, how do you control this flow in the actual plant process? How do you control this flow? Any one of you? We use valves, right? So there are valves which are automated and they control the flow accordingly. So this is in a way is actual plant is controlled by that fashion. In the Aspen Plus, you can use it to define various what if scenarios. This was the basic example. Now, this was just all about mixer and splitters. Then we have separators. So in separators, you have this five option. First is basic separator. This is flash 2. So flash 2 is used for a vapor liquid separation. Flash 3 is used for vapor liquid and liquid like three phase like VLLE. And then decanter is used for separation of liquid stream based on the density. So based on the density difference, you will get two different streams. Then we have separator, which will do a basic fractional calculation, vapor liquid fraction calculations. Okay. So difference between this flash 2 and other separator is like, as I said, that flash 2 separates feed into the two outlets. So one is vapor, one is liquid. While flash 3, you will have three outlet, vapor, liquid, liquid. And these two liquids, like two bottom one, they will have this density difference. Based on that, they will be separated. So if you want simple vapor liquid equilibrium calculation, use flash 2. If you want VLLE calculation, then use flash 3. This flash model, if you were there in the last class, we had done the flash 2 calculations for benzene toluene mixture, ethanol water mixture. So I'm not going to do flash 2 calculations here, but we will take the example of flash 3. And this flash drum we can use for other analysis also, such as evaporators, single stage separators. Now, any of you know the difference between evaporator and flash drum? Like how they will separate it when evaporator is used, when flash is used? Can you think it about? See, flash is used to separate your product into two phases like vapor and liquid. But evaporator is particularly used with the solid system. Like so, to you want to evaporate some solvent and then you will get a solid residue, that kind of a thing. So that way evaporator is used compared to flash. And then you have a separator column, which is a kind of a basic example of distillation column where you can separate your feed into more than two outlets. It's not just vapor and liquid. You can specify three different outlets, like three, four, or n number of outlets. And then you will get this degree of freedom, mn minus n or n minus n. So this is if you will do degree of freedom analysis, you will get this value. So what we will do, we will first consider the example of flash 3. I have already loaded it. So I am considering the example that sir has provided for flash 3, that you have a mixture of feed which has naphthalene, toluene, water and air. They are coming together, they are mixed. So now you have this three phasic system like naphthalene, toluene, water and air. They will create vapor, liquid, liquid equilibrium. And then you use this flash tree to separate vapor or light components which are oil and heavy component which is liquid. So first, if you will go into the property analysis, I have already added this component, air, water, toluene, and then naphthalene. Now, one person in the last class was asking me how to, whatever plot we do, let's say I'm doing some property analysis, how to save the data of that plot. So let me just quickly show you this. Let's select any value, enthalpy of what air I am selecting, and I want to run. So when you will do run analysis, you will get this plot. Now in this left hand side panel where you are doing this plot property analysis, yeah, here analysis pure one. This is the input, and its corresponding result should be here. So you have this result. So if you will select it, right click, copy, then you can paste it in your Excel or anywhere. So similarly, you can save any data, your stream data also directly from this, or any property. Let's say you are doing PXY, TXY calculation and you want to save your data, then you can use it in this way. See, I can just paste it and now I have this data, right? So in this analysis part, you will find with the input, you will find this result. Same way, any simulation data that you want to save it, you can use it in that fashion. So we have added our system, which is like feed, which is mixture of this three component, and add. They are going into the mixture and then separating into the three phases. Let me close this. So go to the stream analysis. Add data I have added based on the problem statement provided. So this is the example that sir has covered, a same example. Then feed, which is a combination of water, toluene and ethylene. It goes to the mixture unit. So for the mixture unit, since it's a three phase like vapor, liquid, liquid, equilibrium, you have to specify it, or else the result that you will get might have some in wrong value which are not physically possible. As we saw in the last part that we were getting temperature value of minus 15 degrees centigrade, which is not possible since the feed has this high temperature. Then it goes to the separator. In the separator column, the desired input are pressure, temperature. So you can specify at what temperature pressure you want to operate your flash, or if you have duty or vapor fraction ready, like let's say you want 0.10% or 0.20% of feed being converted to the vapor, you can use it in that way. So right now I'm keeping it to temperature pressure condition only, and then if you will run it, you will get the results in terms of asset processing. Yeah, result available. So go to the results and stream summary and separated stream summary. So mixture it's separated into three parts: liquid, oil and vapor. If you will see the composition of this part, mass fraction are vapor, which primarily contains the air. Then there are some water and toluene. Since toluene is more volatile compared to the water and ethylene, you are getting toluene fraction in the vapor also. Our oil phase mainly contains the naphthalene and toluene part, and then our heavy liquid part. So water has a higher density compared to this toluene and naphthalene. It is getting separated in the bottoms. So this is the example of flash freedom. Again, it's used for this phase equilibrium calculation. Flash 2 we have already done it, and I think your exam assignment example involves flash 2 calculations this time. So you can try it out on your by yourself and see what various things you can do in that part. Now, in this flash 3 result itself, in this separator part, there are various analysis that we can perform. Okay, let's say I want to add new analysis. HC curve. In this HC curve, I'm adding new curve. Press OK. It will take me to that curve. So let's say I want to see the variation of vapor fraction with temperature or heat duty. So you select one independent variable. Let's say I'm selecting a temperature. additional property that I want to select. So go to this additional property part, create a new property. You can see there is one property set created. This property set doesn't have any value yet. So you can click on it and then provide any physical property. So you will get variety of data. Let's say I want to calculate heat capacity of the system. Heat capacity of the system, and this is the unit qualifies. Just liquid phase. This is coming. Just a minute. Just a minute. Huh? In saturator, let's see. H can do a heat utilization. In the separator. Let's calculate this. If you will run it, so you can see the with the change in the heat duty. So in HC curve, you can change various independent variables. So here I'm changing the heat duty, taking it as a variable, and how the pressure and temperature of system will vary with it. Right now, what we have done is that in this flash 3, we have provided temperature and pressure as input. So let's say I want to see what will be the changes in my system with temperature. So you can select it, run it, and then you can get the data. With temperature, what will be your pressure of the system, how much heat duty will be needed in your flash drum. So that kind of things you can do with this analysis block here itself. So that is the beauty of Aspen Test, that you can try out various scenarios without having to worry about performing actual experiment or doing it in a field itself. Uh, Now, another example in the separator is this decanter column. So why decanter is used? Can any of you answer me? To separator? Yes, right. So let me first step. So extractor is used to separate two liquids based on their density value, where the heavy density product will go into the bottom and light density product will go into the top part. Can any of you know the industry where this decanter are a big part? Do you know any example?
Butadiene and
Yeah.
water.
Can you repeat it again? Sorry.
Butadiene and water.
Butadiene and water. No, apart from that, like if you will go into any refinery, where you know that the raw crude oil that comes after the extraction process itself, it contains crude oil and water. So there they have this very big this separators, decanters present to separate the water and the light key component, light gases from this mixture of crude oil and water. So the this decanter is kind of essential part of any refining industry. Uh, if you have seen or had been visited to that kind of industry. Again, it will take some time to turn it. Let me close it. Not that.
No, sir. Can I say something?
Yeah.
So actually, I'm working in a steel industry, and we are having this decanter used to separate tar and water content.
Hmm. Yeah, yes, that's what I'm saying. Like that is kind of a your in a way essential part, right? So for any refinery industry, as in when extraction happened itself from the offshore, first it goes to its separator unit where water is separated from this oil gas mixture, and even the light gases which are present in the oil are separated in such kind of units. Uh, I wanted to know, is it okay for you guys if I record a simulation first and then just show a video of it during the class, since it's taking time to load and it consumes a lot of time. If it's okay with you guys.
Yes, sir.
Well, okay, thank you. Um, because of some of the work commitment, I was not able to figure out this issue. So I will try it. Else, what I will do, I will just record the simulations, what exactly steps I'm following in the simulation, and then we can see that video and discuss it out. Shubham, you must have received the links to get the PPTs. So in this Swayam portal itself, you might have gotten that link. Have you guys received the presentation and the video lecture link, right? Line sizing and pump sizing session. I'm not sure. So what I'm doing right now is I'm following the uh, method that sir is using, like the various unit operations sir has taught, and I'm trying to kind of give you a recap and few gist of it, because there are various things that he cannot discuss within the given time span. So that's why we are here. Uh, I will try to do if I can touch some aspect of line sizing and pump sizing. Meanwhile, let me show you what I'm seeing. So in this Swayam portal, uh, let's say you have logged in, go to the code, and if you will scroll down, so there are this problem solving session, right? So if you will click here, problem solving session, so you will get this Google spreadsheet where you can find the YouTube link for last week lectures, as well as this is the drive for this presentation that we are using. Similarly, you can find, if you want to check out how other TA, what method Rajdeep is following, you can do that also. So this is the last week PDF. This week PDF will be also uploaded here, and same way you can access the YouTube link also. I hope it's clear. Okay. So for the decanter example, let's say you have a feed mixture here, and we are considering example of mixture of paraxylene and water uh, with a flow rate of 2000 kg per hour coming at 30 degrees centigrade, 1 atmosphere, with equal percentage of paraxylene and water, which is fed into the decanter at 40 degrees centigrade and 1 bar, and just find out whether this how much phase separation will happen. The method that we are using is NRTL using unifact method. So I have added this thing, and this is the layout. So decanter you can find in this separator part. Here, let me go to the feed stream. So our feed is coming at 30 degrees centigrade, 1 atmosphere. Flow rate is 2000 kg per hour, and mass fraction, both water and paraxylene are equally has equal mass fraction values. Now you don't have to provide in the decanter part. Input to the decanter goes to pressure and temperature value. You can provide duty also. Based on the duty part, it will determine how much temperature of the system is running. Now, in the uh, decanter separates the liquid based on the density difference. So ideally, you will get top product as a light and bottom product as heavy. Here you have to specify a key component that will be separated out in the top. So key component to be identified, second liquid phase. So here I have selected water. So that's why if you will see, if I go to the stream results, in the light key component, mass fraction of water. Sorry, water is right now I have selected in the water is currently heavy. So um, mass of water in the heavy bottom product is almost 1000, like 999, while rest of the paraxylene has gone into the top part. Okay, this two value. If I select in this decanter stream, let's say I want to specify, I want water as a kind of a light component, as a key component, and I run the simulation. In that case, what will happen? If you will see the mass flows, the water, maybe I have used, sorry, wrong notation. It should be reversed. Water is coming at 4. Yeah, sorry. So see, decanters, there are two streams. First liquid, which is required. Second is heavy component. So in the required component, I am selecting paraxylene as a light key component. And when I am running it, now we can see the light key component paraxylene is in the bottom and heavy key is in the top. So in a way you can play with this option, but in actuality it doesn't make any difference. So heavy product will come from the bottom only, and while the light product will come from the top. But suppose you have a complex flow diagram present here and then you want to work it out, then you can play with this option and specify heavy product in the top and the light product in the bottom also. That's a simple example of decanter. Next is after decanter, the separator. Separator, I'm not taking it right now. Basically, it's essentially kind of a flash 3 part only, where you have these 3 different sections. Uh, Rather, I will like to go to the heat exchanger part and complete it today because there are some different examples that I have prepared in heat exchanger part. You can try it out on your own. This is the example that Sir has followed. So you have that video link so you can follow him. Now, different at what time we have to which separator to use. Like you have separator to separate various components. Then we have F split. Then we have flash. So each has a different function. So if you want to just divide a stream into various parts without any separation, then you use separator columns that will split the flow without altering the composition of the outlet stream. While FS split, splits the flow, but you can change the composition of the outlet stream. So we can specify. So FS split has various options, as I was saying, that we can limit the flow, we can provide cumulative flow. Based on that, we can manipulate the output. And flash will split your product into two parts, like light key component and heavy key component. So these are the separation units. So you have to understand basic difference then to use what. Coming to the heat exchanger part. So in Aspen Plus, we have this four heat exchanger unit. We have heater, heatex, and M heatex and H flux. So heater is nothing if you want to basically heat a particular stream or cool it down from a desired temperature to a desired temperature without having to put an heat exchange between other steam. So that if you want that, you can use heater. Heatex is to transfer heat between two components. M heatex is for multi component, like multi stream heat exchange analysis, and then HX flux is for LMTD and area calculation. So in a heater, what you do, one outlet heat stream can be specified, and then net load of heater you have to provide. Okay, so there are very less variables in the heater part. Let's say you have some specific steam which is heated by uh, that's heater, or rather there are heating oils also available, and you just want to add a heating duty without any exchange to other process stream. You can use heater steam. But if you want to do a proper heat exchange calculation where two process stream uh, in your plant exchanges heat, then you can use heatex. In heatex, what we can do rigorous heat exchanger calculations. For rigorous calculation, and the geometry of exchanger must be known. So, are you guys familiar with this TEMA standard? What is the full form of TEMA in the heat exchanger? You might have learned in your UG curriculum, right? So TEMA is Tubular Exchanger Manufacturer Association. So they decide various standards for heat exchanger. So based on that TEMA standard, this E, F, G, H, J notation that are used for whether it's segmentation level, the flow arrangement, is it one pass flow on the cell side, two pass, three pass, how many passes on the tube side, that way. So if you don't know it, uh, I will recommend you to search it on the Google. You will find various TEMA standards which are used in the industry, particularly those who are working with the designing field. You must know these TEMA standards. TEMA standard helps you to determine what will be the specification of heat exchanger, specifically the geometry part of the heat exchanger. What we cannot do in this heat ex is the perform the mechanical vibration or the assess the fouling factor calculations. But rest of the calculation we can do it out. And the meta heat M heat ex, unlike the normal heat exchanger, we can do multi-stream analysis there. Let's say we have multiple hot stream, multiple cold stream coming out, and there is a heat exchange happening in between them. Then we can use in that case M heatex. So purpose of M heatex is kind of to do heat integration analysis of the system. Do you guys know the pinch point analysis? No. So pinch point is kind of a minimum temperature difference that you can achieve in your system between the hot and cold stream. So that that is a different aspect of pinch analysis. But if someone wants to do that, then M heatex unit will be useful. And then you have HX flux, which is used for area calculation or electricity calculation. So let's start with a basic example of heater and heat exchanger. I have already this data ready. So we have two streams. One is water stream, one is benzene stream. Benzene is coming at 30 degrees centigrade with a flow rate of 1000 kg per hour, while water is coming at 300 degrees centigrade at 600 kg per hour flow rate. And they are both at two different pressures. Now let's say, first I just want to see the heater analysis itself. So I have this two stream, benzene coming in, it is coming to this heater and then it is going out. So that is benzene out. I have water in coming to a heater and then it's W out. Now you notice this, there is this dash line. So here in the material line, if you will select this option, instead of material, we can provide heat, work or power input also. So I have selected the heat and then let me delete it and show it open. You can connect the heat duty of two heaters. Let's say I want to connect the heat duty of this B1 block to B2 block. I can connect that. So what does that mean? That the heat duty of both the block is same. So energy transfer by done by block 1 will be received by block 2. Let's go to the stream input part first. Right now I am focusing on this part only. We will come to this also. So first is B in, which is benzene in. So benzene is coming at 30 degrees centigrade, 2 bar pressure, 6000 kg per hour flow rate. Add this value. Now benzene out you don't have to specify. That will be calculated based on the heater. See, you can see I haven't provided any. Then folding, not folding, I want watering. Watering. So water is coming at 300 degrees centigrade, 10 bar, and as the mass flow rate of 600 kg per hour. Now, I want benzene. In our problem, it is stated that we want to heat the benzene. So heat duty is 10 kilowatt per hour and it's operating at 2 bar pressure. So let's say the B1 block, input of the B1 block. So we have this various options. Either I can provide pressure, temperature change or pressure drop. So we are selecting pressure and the duty of the system. We can also provide the vapor fraction, degree of superheating, subcooling. So we know that our heater is operating at 2 bar and the duty is 10 kilowatt per hour. So I have selected that. Now, corresponding to that, this heat is transferred to the B2 stream. So if you will open the input data for B2, so you can see here we have to only provide one data. Let's say if I delete this S1 stream, which is an energy stream, then if you will go, you can see this B2 has become red. So it is asking for one more input. So one is pressure and it's asking for temperature value also. Or rather, let's say you can provide duty also. So I can provide that this 10 bar, which is coming 10 bar energy, which is heating this benzene stream, is coming from the water. But rather than that, I can provide them individually also and run the simulation. Results available. So you can see the stream data. For both B in, B out, W in, W out. So benzene is heated from 30 degrees centigrade to 33. Now, here what has happened, that since I'm saying that water is coming to this B2 block, which has a 10 kilowatt per hour heating duty. That's why it's heating water again and its temperature has rise to 329 degrees centigrade. But let's say I don't want that. I want that the water should heat this benzene itself, rather than I don't want to provide it as I don't want to heat the water. I want to in a way cool it down and heat the benzene stream corresponding to that. So in that case, we will use this heat stream and connect them both. So now they are connected. And if you will go to the B2 input again, just check it. It's operating at 10 bar and run the analysis. result available. So you can see here W in, W out. Initially, water is at 300 degrees centigrade and now it has cooled down. So water energy is transferred to the benzene energy. Thus, benzene is right. Benzene temperature is rising from 30 degrees centigrade to 33.39, while water is cooling down from 300 to 270 degrees centigrade. So this is in a way indirect heat transfer between two streams. This can be useful if you are doing cross plant heat integration, where you there is one stream, one hot stream which is available from the other plant that will come to your plant, and then you want to see do the analysis. In that case, you can use such methods, or rather just simple heater or cooler unit, right? Now, if we want to use a heat exchanger, let's say I have a process stream, I have a heat exchanger, so I can do a direct heat transfer in between them. So that's why this heat-ex unit is used. In the heat-ex unit, you have to provide four input output, two input stream. One will be cold in, one will be hot in, and two will be H out. One will be hot out and cold out. That I have added. Let's go to the input data of each. So cold in. Now what will be the cold stream here? What do you guys think? What should be the cold stream? Water or benzene? What we call cold and hot stream in heat exchanger? Can any of you answer it? What should be hot and what should be cold? See, benzene is at 30 degrees centigrade and water is at 300 degrees centigrade. So benzene will it be cold or right? No. Yes or no? Anything? Yes or no? Sorry, I cannot hear properly.
The engine will to cold and water will be the hot.
Benzene will be cold and water will be hot, right? So
Yeah.
hot and cold is not decided based on this temperature. It's like those stream which has higher energy, that will be hot stream, and those stream which has a low energy, it will be cold stream. So anyway, cold stream will be heated and hot stream will be cooled down. So thus our water will be hot stream and benzene will be cold stream. So if you will see hot in, so hot in is water, same temperature pressure condition, and then cold in is water. We don't have to provide the output for this exchanger. That will be calculated. Now coming to the B3 block, which is heat exchanger block. If you will go into the input of B3, setup of B3, you can see one is we can perform a shortcut calculation and another is we can perform a detailed calculation. In this shortcut calculation is kind of just doing an exchanger duty analysis. So right now I have selected that and I want to design it. So I'm providing exchanger duty. So we are saying that 10 kilowatt of energy will be transferred. So exchanger duty is 10. And then there is this option of minimum temperature approach that is selected as 1 degree centigrade. So what is this minimum temperature approach? You must have learned it, right? So minimum temperature, yeah, go ahead. No, feel free to answer it. It's okay. It's kind of interaction session, so you don't have to be very formal or worry about being right or wrong. Okay, let me answer it. So minimum temperature approach, how much difference in hot and cold out?
Smallest temperature difference.
Yeah,
Mm,
less temperature
hot and
difference.
cold.
So what is the general approach of minimum temperature that we select? You might have performed this calculation part in heat transfer or this designing course, right? So what is the general value of minimum temperature approach? Sorry, can
Cooling
you
top is not clean water, clean it
sorry, I didn't got your answer. Can you repeat it?
like cooling tower.
Hmm.
We use as a bed of temperature. I think
Hmm.
for the
Okay. Yeah. So basically, it's like how much minimum temperature difference you can achieve between two fields. So generally, we select the minimum temperature approach as a 10 degree centigrade. That's kind of a basic assumption that you do in this process calculation, right? Uh, but here we have selected one that is just for a learning purpose. Apart from that, what will happen if we reduce the minimum temperature? Let's say minimum temperature difference between hot and cold stream. Uh, it's 5 degrees centigrade. So, meaning if delta T is small, then what will happen to the heat transfer part? Heat transfer will be affected, right? So Q is equal to UA delta T. So let's say you have hot stream coming in from one direction, cold stream going out. So when we say minimum difference, so that is the difference between, let's say, hot inlet and cold outlet. What minimum difference we can achieve there? So we cannot have delta T too narrow also. And if it's too big, then there is no heat transfer happening in the system. If it's too small, then at the end of your heat exchanger, heat transfer will be minimum since the both streams are kind of in a way same temperature level. So right now here we have selected one. You can try it out 10, 5 degrees centigrade and see how the output changes. And when you run it, so after running the analysis, this is stream result. So again, stream result will be same since we have selected the heater duty as 10 kilowatt only. So the heater analysis that we did, that benzene is heating from 32. Is anyone sharing screen? Nani, hello. Are you guys able to see my screen or this person's screen?
Yes.
You are able to see my screen, right? Yeah. So basically, essentially the values are same. But let's say I change the minimum temperature approach. So right now, it- will it affect my result or not? Let's see. Center. Instead of 1, I'm selecting it as a 5 degrees. Running the simulation and see the stream. Again, results are not affected. Why? Because here the difference in the hot and cold stream is very high. Like temperature value of cold stream is 30 and it's going max to 33 degrees centigrade, while the hot stream is at 300 and 270 degrees centigrade. So selecting minimum temperature 5 or 10 won't make much difference. But when you have a very narrow margin between the two hot and cold stream, in that case, selecting minimum temperature approach will have effect on your result. That is one aspect. Now, uh, now here another is, this is the basic shortcut design that we want to do. Here in the shortcut design, you can further specify various parameters. Let's say LMTD. Uh, Generally, LMTD, people in the designing field, they use some correlation also to account for various factors, whether it be fouling factor or the effective heat transfer that is happening. So if you want, you can provide various correction factor to LMTD value. So here calculate the LMTD correlation for exchanges using geometry. Based on the geometry also. So what kind of different exchanger we have? We have Shalom exchanger, we have latency exchanger, we have this air cooled exchanger. So each will have different, based on that geometry, actual LMTD will be different. How we calculate LMTD is based on the difference of two outlet streams, right? So LMTD is calculated by difference of this two extreme, and this is the way we calculate the LMTD. But in actual equipment itself, your LMTD will vary. So if you want to do more rigorous calculation, then you can select such factors. You can also provide the pressure drop on the either side of the exchanger, be it the hot side or cold side. And there are some other methods also. So there is this U method. U is nothing but overall heat transfer coefficient, right? So whether you want to keep a constant U, whether you want to change, like with the phase change, you will have different value. There are some power law models, power law equations also available that calculate the variation of your overall heat transfer coefficient with the flow rate. So such kind of flexibility you have to analyze various output of your heat exchanger. Now, that was the basic shortcut method of heat exchanger. Another is to detail analysis, where you can design this shell and tube plate type or catalog reboiler. Now, my current installed Aspen version doesn't have this extra addition, so that's why I'm not able to compute it. Let's say you want to work with shell and tube only, and uh, you want Aspen to select initial exchanger design, and then we will modify it. But since I don't have this package, I cannot do it. So can any of you share your screen again so that we can check this out? I think Gaurav, can you share your screen again if it's possible to just show you how this heat exchanger design works? So we have two components, water and benzene. The method itself, just a minute. I have selected Unifact method. Select Unifact method. Unifact. You will find it down. Now go to the simulation. Add an exchanger. Type. Connect the input stream of exchanger. Now provide input. So this is S1. S1 is, I think, cold, right? So it will be just a minute. So S1 will be cold in. S2 is C out. S2 is not in. Now provide the stream value for C in. So this is cold in, right? So that is benzene. Benzene is coming at 30 degrees centigrade, 2 bar pressure, and mass flow rate of 6,000 kg/hour. Water is coming at 300 degrees centigrade, 10 bar, and max flow rate is 600 kg per hour. Go next. Yeah. So let's say we have done shortcut. Select on the shell and tube. So here there are various options. One is that you can select initial design from Aspen Plus itself, or you can provide some design if you already have it. Right now we don't know it, so we will choose Aspen Plus method for the designing only. So just click on the convert part. Convert button. Let's click on. Oh, sorry. First run the simulation with shortcut method. Shortcut. No, we still have to specify. Go down. Exchanger specification. We want to provide duty. Exchanger duty. Duty is 10 kilowatt. Now run the simulation. The results are available, so you can see the results. Go down. B1 block. Can you select the thermal result also? The stream results we know. In the thermal result part, you can see the here you can see a hot stream inlet, hot stream outlet. It's similarly cold stream inlet outlet. If you will click on the exchanger details, so in the exchanger details, we will get duty of this, since duty is 10 kilowatt that we have selected. But what will be the required area? What is the heat transfer coefficient to your system? Okay, that thing. Now here we haven't provided any area, so it has calculated area on itself. That's why actual exchanger area and the required exchanger area are same. But let's say if we provide a geometry, then what will be the difference in the actual area and required area that we want to understand? So for that, now we will perform the rigorous simulation of heat X. So can you go again to the heat X part, input part of heat block D1? Now select shell and tube. And do convert. So as you can see, a pop-up window will come where various specification of your heat exchangers are provided. So as I was saying, you must get yourself familiar with the scanner standard. Kind of a that thing. So here we will select few options. In this side, specify some transfer design. Select that option. Share light. We want let's say select the shell ID DL 20, tube length is 100. Baffle spacing as a 5. Actually, Aspen should give some initial data. Can you go into the calculation mode part first? What are other options there to check it? On the top part, That is calculation mode, right? Design initial, then selling seed that one. Selling series 1, parallel 1. Number of tubes you select as 50. Can you put that value? Number of tube as 50. Shell in series 1 and shell in parallel 1.
The number of tubes over here.
Number of tube, put 50.
Unable to put it. It's showing great.
Okay, just sorry. Select wrong. Actually, it should give some initial data. I'm not sure why. Can you see a convert option now? Can you minimize the screen because there are some few options which I want to see at the bottom.
We're going to go down.
So basically, we want to finalize this design. So there should be some option there to finalize this design. Is it possible to minimize this pop-up window? Maybe leave it. Okay. So basically what here you have to do is that once you have this specification ready itself, you can close it if it's not working. Yeah, run start. So once you select various parameters, let's say for heat exchanger, then you want to do sizing analysis, like this rating analysis rather, whether the specification that you have selected is matching with the actual data. See here it has generated some data for you. Okay. So by considering cell ID 20, tube length 100 and baffle spacing, it has provided this design. Can you finalize this design? Confirm somewhere. Accept design. So let's say you have some sort of a initial rough idea of design, or you have some standards based on that you have created. Now in the calculation mode, instead of simulation, click on rating. Rating, and now run the simulation. Yeah. So results are available. Again, go to the first go to the stream summary. So stream summary first. So you can see the since the duty is same, the temperature values are same. Liquid phase is going from 30 to 33. Water is going from 300 Kelvin degree centigrade to 270 degree centigrade. Okay. And the pressure, there is some pressure drop calculated here this time. The rest of the things are almost same. Now can you go to the thermal result part and the exchanger details now. So here you can see the required exchanger area is 0.467 meter square, while the design that we have provided, the exchanger area is 50.58. So that is very heavily over designed, right? So in that case, now we have to modify this design. For that, what you can do, the design that we have selected. So instead of we had selected cell tube cell length of 100, right? Instead of 100, do it 50. Instead of provide bigger diameter of shell, provide a smaller diameter, reduce the number of pass. So that sort of a thing you have to start. Now this kind of a becomes a combined approach of designing as well as optimization. So for our understanding, this is just kind of a no. Okay, these are the various things that we can do with the Aspen Plus in right. But if you want to specifically like rigorously work in this direction, uh, optimization of heat exchanger, design of heat exchanger can also be happening. Can also happen in this. How many of you have done that designing course in your UG curriculum? Any of you? Gaurav, have you done it?
No, sir.
So if you are going to do it, then there are very heuristics that we follow, even for distillation column also. That when flooding happens, what should we do? So if
Scheduled analysis?
kind of a sensitive, in a way you can say sensitivity analysis. Apart from that, I mean each factor has some what should I say? Consequences also. Let's say if I take the example of distillation column, if distillation column diameter is very small compared to your feed flow rate, liquid and vapor flow rate, then flooding chances are also there. Similarly, for pressure of the distillation column, let's say you are working on the vacuum, then you need a higher diameter because for vacuum we need a bigger volume, right? So that sort of a thing is kind of a design in a way heuristic that are rules which are followed based on the observation as well as the like governing scientific fundamentals behind it. Same way if you want for heat exchanger also, changing number of pass per tube side, number of pass per shell side will affect your design. So that way you can optimize it. Uh, if you haven't done this course like this kind of a thing, then we let it be. But I'm saying if any one of you want to do it, these are the things that you can do with Aspen Plus. Okay, thank you, Gaurav. You can stop sharing your stuff. That was all about heat exchanger part. Uh, I'm not getting into the end heat ex part because it's very simple compared to this two thing. We will solve one more problem related to heat exchanger, and then I will try to go through the extractor column example, and then we will do some quiz part. Distillation column part I will try to cover it next time because since what sir has covered in that, I think it will require some recalling of your fundamentals. Then we can work in that direction better. So let's see. Maybe in next lecture I will try to complete the distillation part. So here we have one example. So stream of water is coming at 50 kilomole per hour and 90 degrees centigrade. And there is one more stream of butanol with a flow rate of 20 kilomole per hour and 25 degrees centigrade, which are fed to heat exchanger with operating at atmospheric pressure. And we are using NRTL property method for the simulation. You have to use heat X model. Hot stream will pass from the cell side. The heat exchanger duty and LMTD correction factors are given. So as I was saying that if you want to do more rigorous design and there are some correction factors that you want to apply, you can apply that. So here we have to apply correction factor to LMTD of 0.8 with a minimum temperature of approach of 1 degree centigrade. And the flow direction is counter current, shell side pressure drop is given. You have to use power law model for calculation of U. Okay. And perform a heat X calculation and find this answer. So for that, what we will do, this we have discussed, right? This part and this part. This heat flux unit, it's very simple. So it is used to calculate this. Either you want to calculate the heat transfer coefficient or you want to calculate the area of your exchanger, required area for the exchanger, you can do that. So in this, block B4. This is the setup for heat flux, HX flux part. So you just provide the input stream of hot and cold. Either you provide the duty. Let's say I don't want to compute this. Rather, I have some heat transfer coefficient value. Then when I will do this calculation, it will provide me what should be the area. So if I run it, results are available. So if you will see the B4 block result, for a 12 kilocal per second, this heat transfer coefficient, heat transfer area should be this. So if you want to do a quick calculation of area or LMTD part, you can use this uh, sorry, HX flux part, HX flux B4 part. Anyway, I will close this. Coming back to our problem again. So we want to do a heat X example, sample problem. So this is kind of in line with what you have in assignment 2. Assignment 2 is flash operation. I think that should be relatively easy to do for you guys. So this is in a way same direction that what you are getting in the other assignment. So first let's go to the property part. I have two components, water and butanol. The method that we have provided is NRTL. We are asked to use it. Go to the simulation part. Here, colding. So what will be the colding? We have water coming at 90 degrees centigrade while butanol is coming at 25 degrees centigrade. So butanol is our cold stream that will be heated and water is our hot stream that will be cooled down. Okay. So my cold in is butanol 25 degrees centigrade with this flow rate. My hot in is water at 90 degrees centigrade with 50 kilomole per hour flow rate. In the block part, so we have given that heat exchanger is operating at 40 kilowatt and LMTD correction factor of 0.8 is given. So I have specified the exchanger duty as 40 kilowatt, minimum temperature approach as 1 degree centigrade. In the LMTD part, correction factor of 0.8 is applied. There are other methods also which require different aspects. Like geometry will calculate based on the geometry of your exchanger. Right now we are using this constant correction factor. Pressure drop is also given. So it's mentioned that the flow direction is counter current with a shell side pressure drop of 0.2 atmosphere. So our input is at both of the streams are at 1 bar. Right now I selected 1 bar. So 0.2 pressure drop, that means outlet will be 0.8 bar pressure. Or outlet will be at 0.8 bar pressure. Right? Hot fluid is selected on the shell side, counter current flow is selected. And in order to calculate this heat transfer coefficient, it is mentioned that power law model is used with reference heat transfer coefficient and the desired exponent. So it will use this equation to calculating heat transfer coefficient. And when you will run this result, we will get the relevant data. One is obviously the thermal result, which will give you the specification of your heat exchanger. What is the heat duty, exchanger details, required heat area, actual heat area, heat transfer coefficient, LMTD of your system. And then you have stream result. So what are the questions? First is what is the required heat exchanger area? So that I can find it from this thermal result. And then in exchanger details, you can see, oh, this is the heat transfer area, 0.005519. Is it true here? So my answer is like 0.00 between 0.0056. This is correct. The heat transfer coefficient of heat exchanger that is asked. So you can see average UA precisely. Okay. So my value is 1658 joule per second Kelvin. It should be somewhere between 600 and 700. It's correct. Then the enthalpy of hot outlet stream is asked. Where I can find the enthalpy of hot outlet stream? In the stream summary, you can check. Stream summary, you see, I can find the molar. Yeah, you want to say something? No. Okay. So molar enthalpy of the system, you can find it. You can change the unit also. We want joule per kilojoule per mole. So that value is minus 282. Is it? Minus 284 to 284. Then if we reduce the heat exchanger duty by 20 kilowatt, what will be the exit temperature of the fluid? How much area will be reduced? So I will go to the setup model, and let's say now instead of 40 we want 20 kilowatt of heat duty and run it. Then in that case, outlet of the hot stream becomes 71. So it has changed now. Previously it was more like less, now it's then the reduction of the required heat exchanger area. So heat exchanger area will reduce or actually increase. It will reduce, right? Since the heat duty is reduced, so required exchanger area will go down. So current exchanger area is 0.0017 and previous was 0.0055. So that difference will compare around in between 0.0035 to 0.0035. So these are the basic kind of assignments questions that you will get, and that are relatively easy to solve also. I'm skipping this column part. Maybe we can take it next time, both the column part. So in the column, we have option of DSTW, distill and red flag. These are three distillation units. While red flag we can also use for reactive distillation and the adsorption part. So first, DSTW is very basic distillation column method, which will provide you number of stages, minimum refractory ratio. And then distill and red flags are more rigorous calculation, where we can see the each internals, like we can specify the internal parameters of distillation column and analyze the flooding aspect, operability of each aspect. So that I will, what I will do, again, so that's why I'm asking that how many of you are familiar with the concept of distillation designing, flooding and treatment, this distillation column internals, downcomer sizing, that sort of stuff. Can I just get a count, yes or no, kind of a thing? So 1%. So rest of you, 2, okay. Yes, only 2, 3 people. So are you guys currently UG student, second year, third year? Maybe because of that you haven't studied it.
Yeah.
Okay,
The third year.
Yes, second.
second. So then going into that details will require more of your understanding. So right now that's why I haven't gone into that detail, but because I found that this separator, heatex and mixer splitter was very basic, which you can understand and try various things out on your own. Even in the heat exchanger design part, the detailed design of heat exchanger, that will require some understanding of various component of heat exchangers, what will affect what. Same for distillation column also. Maybe what I will try to form some basic theoretical background. We can see some example and then move forward without going into too details of it. And those who want to understand it, maybe they can try it on their own. Is it fine? I assume it's fine.
Yes.
Okay. Yeah. So this column example take next time. So I had planned the extraction problem and the basic distillation column problem, but that we can look in the next time. Let's start with a small quiz of how much you have understand, and again this will be kind of related to the what kind of assignment questions you have. So in Aspen Plus, which of the unit operation commonly separates component based on their boiling point? So which of this will separate component based on their boiling point?
Destination.
Yeah, distillation. Now, what is the purpose of reboiler in distillation column?
Image liquid fit.
With the liquid feed.
Yeah, to heat the liquid. Correct. What is the function of condenser?
Then the mix.
Cool and
Vapor.
compress the vapor. Yeah. Now, which of the following can be used to calculate overall heat transfer coefficient of the process? So we have four options in heat exchanger.
Heat X. Heat X. Ops.
No, I'm just overall heat transfer coefficient of the process without doing much. So in that case, I can use HX flux. You can also use heat X also, but then it will be more rigorous calculation. Here you have to just provide inlet outlet temperature of hot and cold steam. Then based on the area provided, you will calculate the it will calculate just heat transfer coefficient. So it's a basic unit. Obviously, heat exchanger is also useful for that. Now, what is the purpose of absorber in the absorption process? Now, we didn't.
The gases from vapor.
Yeah. Now, which of the Aspen Plus tool is used for designing and simulation of absorption columns? Again, we haven't touched this aspect, but maybe Sir has covered, so if you can answer.
Absorb. Maybe absorb.
Do we have absorb unit there? Have you seen it? It's actually red flag. So as I was saying, that red flags allows you to do multiple calculations. If you will see in the Aspen Plus software itself, there is no absorb unit. And so in red flag only you can calculate, you can do this absorption calculations. So you compare two simulation for the same separation with different reactions. How result will differ? And again, I haven't touched into that aspect, but let's say you have two simulation results for the same separation with different tray efficiency. So what all the things can vary if your tray efficiencies are different?
All.
Yeah, all of the above, because high
All of the above.
yeah. So high efficiency can affect your product purity. Like higher the efficiency of your tray, higher will be the productivity. Better will be the vapor liquid separation. If it's higher efficient, then better vapor liquid separation. So low energy consumption on the reboiler and condenser part. Okay. Similarly, less number of threads will be required. Now, if I increase the reflex ratio, how it will affect the purity of your distillate? Will it increase or decrease?
Increases. Increases. Increases.
Yeah.
Increases.
Now, how can you diagnose and troubleshoot flooding in the pack column? I guess you don't know, as in the answer.
Liquid hold up. Hold up in each space.
No,
The radiation.
actually, there are two correct answer. One is like you can reduce the packing density. Since flooding is happening, so that means that the separation is not happening very well, and then there is an accumulation of your liquid. That's why flooding is happening. So you can reduce the packing density. That will allow ease of the flow, and you can try various different packing ones. Liquid holdup doesn't come into the case of the fourth column. That will come into the case of distillation column, like tray column. If you have trays, then you have to think about liquid holdup at every stage. Then you decide the down common height for the liquid holdup, right? For packing, it's like a type of the packing density of the packing. You cannot increase the pressure drop because of the flooding. Anyway, pressure drop across top and bottom part will be very high. So that's not the answer. So C and D are the correct option. Let's say for a better control over split fraction, which one we will use? S split or F split? Like sorry, I mean statement is whether it's correct or not. Should I use S split over F split for a better controlling of split fraction? Yes or no?
Good.
No. Like, oh, actually, it should be
So
false.
can you please
It should be
explain
false.
this question?
Huh? Sorry.
Can you please explain this?
So I'm saying, so in the splitter part, we saw these two options, right? One is F split this, and another is S split. So if I want a better control, which should I use? Like, I have one mixed string which will be separated via, which can be separated by both of this compound. Like, either I can use F or S split. So if I want a better control, should I use first one or the second one? Actually, it should be F split. Why? Because see, if we will go into the input of B2, actually we have to provide this key. Let me just like, entering random values right now. Now both of the stream has input connected. Let's say I want B2 stream to, I mean B2 is F split. So if I look into that, I am splitting it into two parts. Same via B3, I am splitting stream into two parts. So setup of B2. Now you have asked, they are asking for how you want this separation. So my S1 stream comes to the F split and I can divide it into S3 or S4. Now, how I want to separate them. So if I go into the input parameter of B2, F split, it provides me this multiple option. I can provide split fraction, let's say 50-50 or zero point 0.5, sorry, zero point 0.2 and zero point 0.8 should go in the S4. I can provide the flow rate values, volumetric flow rate, and there are this option also, limit flow rate, cumulative limit flow rate. So as I was explaining that if you want that regardless what happens, what fluctuation happens in S1, you want some specific flow in S3. S3 could be going to your product, your storage unit. It could be going into your recycling unit. And let's say there is some disturbance in input stream of S1. Instead of 1000 kg flow rate in S1, now it has become 800. But you still want that regardless of what has changed in S1. Let's say I want to maintain 700 here. So what this will do, it will prioritize S3 first and then it will look for S4. So if I'm saying S3 should be 700, I'm limiting the flow of S3 to 700. So what it will do is, let's say flow fall down to 700. So it will go first S3 only and S4 will be 0. If from 1000, so I mean you have better control. While if you will look at the FS split unit, this one, if you will go into the input part of that, there are only two options, either flow or split fraction. So it's basically it will divide it into the whatever amount you have provided. But this can be used for different what if analysis, maintaining flow at particular directions. So here actually answer should be false. For better control, we should use F split, not the other way around. There was this one question which I forgot. Um, yeah, anyway, let it be. So this is the end of the class from my end. I will upload this PPT today, and the YouTube lecture will be uploaded by tomorrow. So if any of you have any doubt, we can discuss it out. And in general, you can provide me feedback also, like the way I'm teaching, or is it okay with you? Want some modifications, or there are some specific things from sir's lecture that you want to learn more? Then you can communicate with me via email or via LinkedIn. I will be available. So I'm in a way open to suggestion also, right? So do you have anything you want to say or discuss? Okay, so I will stop the recording.